An atmosphere is a layer of gas or layers of gases that envelope a planet, and is held in place by the gravity of the planetary body. A planet retains an atmosphere when the gravity is great and the temperature of the atmosphere is low. A stellar atmosphere is the outer region of a star, which includes the layers above the opaque photosphere. Stars of low temperature might have outer atmospheres containing compound molecules. The atmosphere of Earth is composed of nitrogen, 78%, oxygen, 21%, argon, 0.9%, carbon dioxide, 0.04%, and trace gases. Most organisms use oxygen for respiration. Lightning and bacteria perform nitrogen fixation to produce ammonia that is used to make nucleotides and amino acids. Plants, algae, and cyanobacteria use carbon dioxide for photosynthesis. The layered composition of the atmosphere minimizes the harmful effects of sunlight, ultraviolet radiation, the solar wind, and cosmic rays to protect organisms from genetic damage. The current composition of the atmosphere of the Earth is the product of billions of years of biochemical modification of the paleo-atmosphere by living organisms. It was generally believed around 5 billion years ago, the Earth collided with a planet the size of Mars. Then by around 4.6 billion years ago, almost no atmosphere was found on the planet, as it was covered by rock of molten lava. However, when the planet cooled, the atmosphere began to develop from gases spewed from volcanoes, which included much of the carbon dioxide. 500 million years ago, the Earth's surface began to cool when the atmosphere was solidified and layered with rich oxygen in order for water to collect on the surface for the evolution of life. To this day, many planets beyond Earth contain a rich pressure with an outermost layer of extraterrestrial atmospheres. Earth's atmosphere refracts sunlight with a day longer than 12 hours in equinox, in absence of its effects of climate change. As early as 2020, with the discovery of the exoplanet TOI 700d, there is a feasibility for an Earth analog with its own atmosphere to be retained. The initial gaseous composition of an atmosphere is determined by the chemistry and temperature of the local solar nebula from which a planet is formed, and the subsequent escape of some gases from the interior of the atmosphere proper. The original atmosphere of the planets originated from a rotating disk of gases, which collapsed onto itself and then divided into a series of spaced rings of gas and matter that, which later condensed to form the planets of the solar system. The atmospheres of the planets Venus and Mars are principally composed of carbon dioxide and nitrogen, argon and oxygen. The composition of Earth's atmosphere is determined by the byproducts of the life that it sustains. Dry air, mixture of gases, from Earth's atmosphere contains 78.08% nitrogen, 20.95% oxygen, 0.93% argon, 0.04% carbon dioxide, and traces of hydrogen, helium, and other noble gases, by volume. But generally a variable amount of water vapor is also present, on average about 1% at sea level. The low temperatures and higher gravity of the solar system's giant planets, Jupiter, Saturn, Uranus and Neptune, allow them more readily to retain gases with low molecular masses. These planets have hydrogen-helium atmospheres, with trace amounts of more complex compounds. Two satellites of the outer planets possess significant atmospheres. Titan, a moon of Saturn, and Triton, a moon of Neptune, have atmospheres mainly of nitrogen. When in the part of its orbit closest to the Sun, Pluto has an atmosphere of nitrogen and methane similar to Triton's, but these gases are frozen when it is farther from the Sun. Other bodies within the solar system have extremely thin atmospheres not in equilibrium. These include the Moon, sodium gas, Mercury, sodium gas, Europa, oxygen, Io, sulfur, and Enceladus, water vapor. The first exoplanet whose atmospheric composition was determined as HD 209458b, a gas giant with a close orbit around a star in the constellation Pegasus. Its atmosphere is heated to temperatures over 1000 K, and is steadily escaping into space. Hydrogen, oxygen, carbon and sulfur have been detected in the planet's inflated atmosphere. The atmosphere of Earth is composed of layers with different properties, such as specific gaseous composition, temperature, and pressure. The lowest layer of the atmosphere is the troposphere, which extends from the planetary surface to the bottom of the stratosphere. The troposphere contains 75% of the mass of the atmosphere, and is the atmospheric layer wherein the weather occurs. The height of the troposphere varies between 17 km at the equator and 7.0 km at the poles. The stratosphere extends from the top of the troposphere to the bottom of the mesosphere, and contains the ozone layer, at an altitude between 15 km and 35 km. It is the atmospheric layer that absorbs most of the ultraviolet radiation that Earth receives from the Sun. The mesosphere ranges from 50 kilometers to 85 kilometers, and is the layer wherein most meteors are incinerated before reaching the surface. The thermosphere extends from an altitude of 85 kilometers to the base of the exosphere at 690 kilometers and contains the ionosphere, where solar radiation ionizes the atmosphere. The density of the ionosphere is greater at short distances from the planetary surface in the daytime and decreases as the ionosphere rises at nighttime, thereby allowing a greater range of radio frequencies to travel greater distances. Moreover, located in the thermosphere is the Kármán line at 100 kilometers, which is the boundary between outer space and Earth's atmosphere. The exosphere begins at approximately 690 to 1000 kilometers from the surface, and extends to roughly 10,000 kilometers, where it interacts with the magnetosphere of Earth. Atmospheric pressure is the force, per unit area, perpendicular to a unit area of planetary surface, as determined by the weight of the vertical column of atmospheric gases. In said atmospheric model, the atmospheric pressure, the weight of the mass of the gas, decreases at high altitude because of the diminishing mass of the gas above the point of barometric measurement. The units of air pressure are based upon the standard atmosphere, ATM, which is 101.325 kilopascals, 760 torr, or 14.696 pounds per square inch, psi. The height at which the atmospheric pressure declines by a factor of E, an irrational number equal to 2.71828, is called the scale height, h. For an atmosphere of uniform temperature, the scale height is proportional to the atmospheric temperature, and is inversely proportional to the product of the mean molecular mass of dry air, and the local acceleration of gravity at the point of barometric measurement. Surface gravity differs significantly among the planets. For example, the large gravitational force of the giant planet Jupiter retains light gases such as hydrogen and helium that escape from objects with lower gravity. Secondly, the distance from the Sun determines the energy available to heat atmospheric gas to the point where some fraction of its molecules' thermal motion exceed the planet's escape velocity, allowing those to escape a planet's gravitational grasp. Thus, distant and cold Titan, Triton, and Pluto are able to retain their atmospheres despite their relatively low gravities. Since a collection of gas molecules may be moving at a wide range of velocities, there will always be some fast enough to produce a slow leakage of gas into space. Lighter molecules move faster than heavier ones with the same thermal kinetic energy, and so gases of low molecular weight are lost more rapidly than those of high molecular weight. It is thought that Venus and Mars may have lost much of their water when, after being photodissociated into hydrogen and oxygen by solar ultraviolet radiation, the hydrogen escaped. Earth's magnetic field helps to prevent this, as, normally, the solar wind would greatly enhance the escape of hydrogen. However, over the past 3 billion years Earth may have lost gases through the magnetic polar regions due to auroral activity, including a net 2% of its atmospheric oxygen. The net effect, taking the most important escape processes into account, is that an intrinsic magnetic field does not protect a planet from atmospheric escape and that for some magnetizations the presence of a magnetic field works to increase the escape rate. Other mechanisms that can cause atmosphere depletion are solar wind-induced sputtering, impact erosion, weathering, and sequestration, sometimes referred to as freezing out, into the regolith and polar caps. Atmospheres have dramatic effects on the surfaces of rocky bodies. Objects that have no atmosphere, or that have only an exosphere, have terrain that is covered in craters. Without an atmosphere, the planet has no protection from meteoroids, and all of them collide with the surface as meteorites and create craters. Most meteoroids burn up as meteors before hitting a planet's surface. When meteoroids do impact, the effects are often erased by the action of wind. Wind erosion is a significant factor in shaping the terrain of rocky planets with atmospheres, and over time can erase the effects of both craters and volcanoes. In addition, since liquids cannot exist without pressure, an atmosphere allows liquid to be present at the surface, resulting in lakes, rivers, and oceans. Earth and Titan are known to have liquids at their surface, and terrain on the planet suggests that Mars had liquid on its surface in the past.